Okay. Good evening. Oh, I got your, yeah. Huh? Oh, yeah, no. But I mean the resume, too. Yeah, I'll look around. No guarantees, but... okay. Well... here we are. Good. Thank you. Oh, yeah, now I know. Oh, yeah. Now I know who you are. Hi. Welcome to the disco. Oh, shoot. A couple of, are we on yet? Wait, I'll wait for him. Okay. Make sure we're on the air. Okay. I think that's over there. Camera's off a little bit. Yeah.
Professor, would you like it on the overhead camera or the rear camera?
I guess overhead, yeah, overhead. Well, it looks like we're on. So a couple of announcements. I did get the grader finally give me back the projects. So I am going through those. Now, I don't want to, this, no. What is going on the overhead? Well, all right, he's working on that. Oh, yeah, I still want to go through those.
Move it back to the other side, or?
To here, so that it's on the right here.
Just zoom in.
Yeah, right on that. Thank you. But like, for instance, she just kind of give me some idea. Well, no, she actually graded the projects, but there were some parts that, like, for instance, extra credit. A lot of students did the extra credit, but some worked it all the way, others didn't. But she didn't know how much to give for that. So I am oh, perfect. I am regrading. Or I don't know if you can say regrading, but just looking it over. So bottom line is, odds are you'll get a higher score after I've done. So I will have those back to you next week now that she's finished. I'm sorry about the delay. The other thing, too, that I want to point out is, yes, there will be a second class project. And the only reason why I haven't sent it out is because we've only really covered sampling since the midterm. So I kind of wanted to get some other topics, but in the interest of time, we only have 3 more lectures. I will make sure I get the second class project out this week, and undoubtedly another homework set. This last homework set, number 4, that you did, that was based on the basically part 1 of sampling. I'll probably have a couple of problems on part 2. And then, hopefully, we'll get it to it today. We'll really have a lot of material to cover on DFT. But unfortunately, by the time I get there, we have, by the time I get to the DFT, we don't have a lot of time. So, in any case, whatever it is, you will see a project, I promise, this week. I will send out the second and final class project. Okay, so from last time, we talked about, basically we went through the, what I called sampling part 2, which dealt primarily last time with, let's see, where was it? I guess that was it, sampling part 2. Which dealt primarily, this was still sampling, yeah. So we finished, last time we finished the sampling part 1 notes, which included the sampling theorem, which even did 2 lectures ago. And then last time we talked about digital upsampling and downsampling. In other words, how you would actually upsample or change the rate of a signal by a rational number, or multiply or divide by an integer. We talked about how to do that all digitally without having to resample it with an A to D converter. So that, and I mentioned last time a MATLAB routine called resample, and let's see if I can find that. Yes, here was a little section of code that I give you in the notes for just basically, in this case it was for upsampling a signal. And if you recall, the trick for upsampling was that you had to go through a rate expander, which just added a bunch of zeros in between samples. So generally, like I said here, the idea, if your input data rate was coming in at 1 megahertz, just take a number, and we wanted to upsample that to 10 megahertz, then you would actually generate a clock 10 times the original clock, and it would pull out samples as they come in at 1 megahertz, but obviously it'll run out of samples, and when it does, you just stuff zeros. So that's what we called a rate expander. It basically expands the rate, the sampling rate of the signal, and when it doesn't have samples, it just puts zeros in. And then, and as we discussed last time, what that does is that produces images of the signal that you want. So you have to low-pass filter that to get rid of the images, and then that is your resampled signal. And this was a way to do the whole thing in MATLAB. And this was kind of a simple loop that would, or not a loop, but a simple routine that would do that. And MATLAB also has a built-in function, which I use a lot, called resample. And the resample function will take a signal, resample of x, comma, L, comma, M, and if M is 1 and L is some integer, it'll upsample it. If L is 1 and M is some integer, it'll downsample. But all the filtering in resample is built in and can be chosen based on some of the input parameters. So anyway, that was upsampling. We talked last time about downsampling, which was simply consists of 2 parts. Here it is, 2 parts. One was low-pass filtering first to prevent aliasing, and then just taking every nth sample, and that's what downsampling was. And we didn't derive, but we introduced a formula so that if you take a signal x of n and you take every nth sample through this operation, x of n L, what it, in the DTFT domain, that produces images. And if you want to do this without introducing any aliasing, digital aliasing, then you will low-pass filter first, and then you will do the subsampling operation. So we talked about that last time. Then we did get into sampling part 2, and we mentioned, or we introduced the concept of polyphase filters, which are just a handy-dandy way of doing operations at a much lower rate. That's what polyphase filters do. So here was a picture. Oh, and then we introduced an important theorem or lemma, I guess you could call it, that came in handy when we did downsampling or upsampling. But here was the basic polyphase filter architecture. If we want to, kind of hard to see here, but we take an input, we filter at HY. we can expand this into these operations. We can expand it like this by simply taking x, delaying, well, taking it, running it through filter 1, delay by 1 sample, through filter 2, delay by L samples, through filter L. And we define what these filters were. These were basically the polyphase components of our input filter H. And we defined what that was last time. And then we talked about ways of decimating, doing decimation. Remember, the decimation operation was first take x of n, filter, and then subsample. And we came up with this nice little architecture. Actually, this was not, there it was, this architecture which enabled us to do all the filtering, even though with downsampling, it appears that you have to, with downsampling, it would appear that you would have to do the filtering at the high rate. It turns out by using some identities, we can, and a polyphase implementation, we can actually do any filtering operation at the low rate. And as I pointed out, or I think I was when the class ended, I took an example where I wanted to decimate by a factor of 10, and my input sampling rate was 10 megahertz, and my anti-aliasing digital filter was an FIR filter with 100 coefficients, and the input sampling rate was again 10 megahertz. As I pointed out, if we were going to do this using the conventional architecture where we have to filter at 100 megahertz with 100 coefficients, it would require a couple of gigaflops, gigafloating point operations per second. But with the polyphase, with this implementation, I worked through some of the, now let's see here. Hang on, wait a minute, something's amiss. No, hang on here. I don't want to lose, there it is. Okay, so that's kind of where we'll start. As I pointed out, if you use the polyphase decomposition filtering approach, I calculated that it would take, instead of 2 gigaflops, it would take a factor of 10, smaller than that with this architecture, 200 megaflops, floating point operations per second. That basically adds or multiplies. So that is a reduction in processing speed by a factor of 10, not bad. And that's why people use this polyphase filtering, especially when they want to do decimation. I'll talk about a different structure in just a little bit tonight. But in any case, that's why you would want to do polyphase filtering in the application of decimation. It really dramatically reduces the computations and the computation rate. And pretty much it does it in 2 ways. As I mentioned last time, just let me read straight. It does it in 2 ways. One, by doing that identity, you are now, once you go through this, and everything from here back is at the high rate, but from here on is at the low rate. So all of these filtering operations are being done at the low rate. And the other nice thing is that these polyphase components of the filter H, they are each of length roughly 1 over m, which is 1 over 10th. So these are much smaller. So these are smaller by smaller. So instead of by 1 over m, and they're done at the slow rate. So these coefficients are, these filters might have only 10 coefficients, whereas the original filter, as we know, had 100, and also they're sampling at the low rate. So you put those together, and it's pretty dramatic in terms of the reduction. In fact, you might think that, gee, if that's 1 over 10, and you're sampling at 1 over 10, why wouldn't you get a 1/100th or 100 times improvement, but instead of just a factor of 10? But the reason why you don't is that you have m paths that you have to do this. Now, what I want to encourage you to do is go through this computational example that I did here in pages 5 and 6 of the Part 2 notes. Please, it's very important you go through those and you understand how I arrived at this computation. Because you may very well see a problem on complexity, because people say, how could you put any problem like this on the final? I mean, you know, you need a computer. True, but you could put a problem involving just simple calculations of like complexity, if I give you an example like this, or a more involved example. So make sure you understand how I went through this complexity computation. So again, on pages 5 and 6, I encourage you to review that for the final. That's a good one. And the other thing, oh yeah, the other thing too is that just like for decimation and the one polyphase decomposition, there's another polyphase decomposition based on upsampling. And here is again what we want to do. We want to go x of n, go to the rate expander. Now you clock everything out at the higher rate, factor of L higher, and then you go through the filter. But you can equivalently do this using this polyphase decomposition. And this uses, actually this uses another one of the identities. There were two that we talked about. And you can see here x of n comes in. There are no delays. It's split into, in this case, L paths, where L is the upsampling factor. And each path is filtered by a filter E0, E1. These are the polyphase components of H. They're 1 over L smaller in length, and they're done at the slow rate. And then those are upsampled with this rate expander, and then the delays are on this side. So that's another way of doing upsampling, and it's also a factor of L, less computation. So those are good little filtering results, especially if you want to, or if you need to do a filter. Now what I want to talk about, there was a problem kind of related to this a little bit on the fourth homework set, and so I thought I would talk to you about basically what is called bandpass sampling. Bandpass sampling. It's a cute little trick. It's just a couple of pages in my notes. Here, bear with me. These are just don't want to make. I want to make sure I don't leave out any juicy information for you. Okay. Bandpass sampling, and these are also in these are in the same set of notes as the polyphase filters are. I kind of combine a lot of concepts together. Okay, but here's the idea. I want to tell you about a really nifty idea called bandpass sampling. We kind of saw an example of it in the fourth homework set, the last problem, but this is the basically along that concept. To illustrate the basic concept, suppose we have a continuous time complex signal. Now this is what I give you in problem 4 of the fourth homework set. And the continuous Fourier transform looks like this. In fact, this is exactly. It's just, you know, the triangle is just something convenient. I mean, it could be anything. But I do want it to be band limited. And I want the maximum bandwidth, oh here, delta omega. I want that delta omega. Now the way I've drawn it, this is so it starts at f naught, some frequency. Presumably that's going to be very high frequency, and then it's going to more or less go out here to f naught plus this omega max over 2 pi. Okay. No, I'm sorry. No. No, this is, sorry, this is f max, forget that. This is omega max, which is equal to f, oh boy, f max over 2 pi, now they call, now they text, f max over 2 pi. Now, the bandwidth of this in radians per second is what I'm calling delta omega. So from here to here would be delta omega over 2 from here to here would be delta omega over 2. The total extent of this bandwidth is delta omega. So what is omega max? Well, omega max is F max over 2 would be equal to omega naught plus delta omega over 2. See? Omega naught plus delta omega over 2. Or if you want to use it in terms of frequency, F max, which is omega max times 2 pi, would equal, what did I call that? No, I'm sorry, F max would, no, this isn't right, sorry. It's times 2 pi. So F max is omega max divided by 2 pi, and that would equal F naught plus delta omega over 2 times 2 pi. Okay? That would be your highest frequency component. Like I said, it's similar to the setup in the fourth homework set. So if we wanted to sample this, just take this, we want to sample it without aliasing, then obviously you would have to pick a sampling rate, F, which would be greater than 2F max, see? Now, the problem comes into play if maybe at delta omega, maybe the bandwidth here is like 10 kilohertz. It's a narrowband signal, but it's centered at, so an example would be delta, example might be, do I have an example? No. Would be delta omega divided by 2 pi. Maybe this is 10 kilohertz. By the way, if I can't really see behind me, if I run off the edge here, let me know. Delta omega over 2 pi might be 10 kilohertz, but omega naught over 2 pi equals F naught. Maybe that's 1 gigahertz, something crazy like that, see? So basically, this is a very, its bandwidth, we could say, is generally a small fraction of the center frequency. That's what I would call a narrowband signal. Thus, x sub c of t is band limited with bandwidth delta omega radians per second, or delta omega by 2.5 hertz, by delta omega divided by 2 pi in hertz, and is centered at the carrier frequency, 2 pi f naught radians per second, or f naught hertz. We can therefore express x sub c of omega as x sub c. And if you look at the fourth homework set, this is exactly what I did. X sub b of omega minus 2 pi f naught. Okay? So when, so we can do that. So when, for instance, omega is equal to 2 pi over f naught, that corresponds to x sub b of 0, see? So x sub b is a signal whose FFT is, or CFT rather, is centered around omega equals 0. Okay? And I think, okay, I'll show you, I have a picture of it, I'll show you in a sec. So thus x sub c of t is a band limited signal. We can express x sub c of omega as this, where x sub b is called the baseband spectrum. I'll show you that sample in just a second. So the maximum frequency in x sub c of t is, as I just said, f naught plus 1 over, in hertz, is f naught plus 1 over 2 pi times delta omega over 2. Okay? That's what I had set up here. All right? But suppose we were only interested in x sub b of omega, the baseband signal. X sub c of t. So we can write x sub c of omega as a function of a baseband signal. X sub b of omega is going to be equal to 0 for absolute value of omega greater than delta omega over 2. Okay? So this is a it has a bandwidth equal to delta omega. So in this case, and it's centered at omega equals 0, right? So in this case, if I use my example of delta omega over 2 pi equal 10 kilohertz, this would have a bandwidth plus or minus 5 kilohertz centered at omega equals 0. This is the non-zero. This is the rest of it's non-zero, okay? So sometimes you might just be interested in this, all right? So let's see what this is in the time domain before we go on. Let's relate x sub b, the baseband, to x sub c in the time domain. Suppose we were only interested in x sub b, what I'm calling the baseband signal. It's because it's centered at omega equals 0. Given x sub c of t, we can generate x sub b of t as follows. Okay? If you can read that. But basically, it's x sub b of t is equal to x sub c of t times e to the minus 2 pi f naught times j times t. See? So this is x sub b of t. Again, it's centered at omega equals 0. And this is what contains all the useful information in this very high frequency input. See? So everything's contained right here. Everything else is 0, or approximately 0 in practice. So the only information that we have is right here. Now, if we want to preserve, when we do the sampling, if we want to preserve all of these zeros between 0 and omega naught, then yes, we have to sample the signal at a frequency greater than 2f max, where f max is f naught plus delta omega over 2 times 2 pi. But this really is an overkill if we're only interested in this piece, see? So if we're really only interested in the information contained in this quote baseband signal part, then we don't necessarily have to sample at this high rate, see? So x sub b of t in the time domain is related to this just by a shift in frequency. You just multiply x sub c times e to the minus 2 pi j f naught t, and bingo, you have x sub b of t. X sub b of t is called the baseband signal, and it's used a lot in communication, speech. Typically in communications, we generate the baseband signal first. So in speech, or I should say in communications or in speech, we might generate, we have some signal, maybe it's a bit stream, I'll call it B of t, goes in and generates the baseband signal, and so out comes the, I will call it x sub b of t. Now, if this were communications, for COM example, we might have that x sub b of t is equal to summation n times, I don't know, let's call it a sub n, p of t minus n times t. Now, we'll come back to, I'll call that t sub s. We'll come back to this when I talk about which I'm not going to cover that. Oh well. Anyway, this is the baseband signal. This P of t is just equal, that's the baseband pulse. Yeah, I guess you can see this. It's equal to 1 for 0 less than t sub s, and 0 otherwise. Okay? That's a way that you make a communication signal. The a sub n in a binary communication system is just plus or minus 1. If it's for binary, if it's QPSK, if any of you have had COM or had that, then these are plus or minus 1 plus or minus j, for instance. But anyway, however you look at it, this is basically the baseband. This is the baseband signal in communications. But this, we typically want to, I mean, we're not going to send this baseband signal over a channel because its frequency content is right around omega equals 0. So what we will do is we'll multiply it before we send it out times f naught times e to the minus 2 pi j f naught jt, or if you don't like the complex thing, then you could take the real part of that And that is what actually goes out. That's what I'll call x sub c of t. Okay? So that's a good example of the baseband signal and then the final signal that goes through the channel. Because most channels, if they're at S-band, you know, they might be centered around 2 gigahertz. If they're at X-band, they might be centered around 8 or 9 gigahertz. So most of these channels, like in the deep space network, uses S-band or X-band or maybe even Ka-band. So you ultimately have to recenter this baseband signal up at a higher frequency. But generally, when you demodulate, when you receive the signal, the first thing you typically do is get rid of this. Sorry, jeez. What the hell is this? Huh. It's my boss. Oh well. Let me turn. I'm going to take that call. Hopefully I don't get fired. The boss. Anyway, can anybody remember, what was I talking about? Oh yeah, that's right. So, but at the receiver end, what you would do is you would, first of all, you take the signal at 2 gigahertz or whatever it is, get rid of this carrier by mixing it down, and then you would recover this baseband signal. So that's sorry I dwelled on that a little bit long. So in fact, here's exactly what I was talking about. So here comes your signal up at whatever the carrier is, and the first thing you do is get rid of that carrier. See, you would multiply it by, you'd multiply it by e to the minus 2 pi jf naught t, and then you would low pass filter it, and voila, out would come your baseband signal. See? And then what you would do is you would sample the baseband signal at a sample rate, fs, which now has to be only greater than or equal to delta omega over 2 pi, see? Because that's half the max frequency. Remember, the x sub b has frequency between minus delta omega over 2 and plus delta omega over 2, or that over 2 pi. So if you wanted to sample this at twice its maximum frequency, so max frequency here, the max bandwidth, is equal to just delta omega over 2, not delta omega over 2 plus omega naught. So now all you have to do is sample that with a sampling rate that's twice that, and in hertz that's this. And then voila, out comes your rate. So in the example I chose earlier, this was F naught was 1 gigahertz, and delta omega naught over 2 pi was 10 kilohertz. So all you would have to do is sample this at 10 kilohertz, because you don't care about the other stuff. All you care about is the baseband. The low-pass filter is called an anti-aliasing filter, and is used to get rid of any unwanted frequency components. Now, if the input spectrum really looked like this, which was 0 with just this little blip, then you wouldn't even need the filter, you know, and everything here is complex. Yes, there is a real equivalent of all this, okay? But we're going to, for sake of this illustration, we're going to stick with complex signals, and then I'll mention something about the case of real signals in a little bit, okay? The low-pass filter is called an anti-aliasing. We wouldn't even use it if there was no noise, but if there is noise, then you do need it. Now, we sample A to D at twice the highest frequency without aliasing, but notice the highest frequency is now 1 over 2 pi delta omega over 2, so the new sampling rate is this, just as I put up there in the figure. This is a much easier requirement than before. Tell me about it. I mean, in that example, it's sampling at 10 kilohertz versus, gigahertz. Okay. But this method still requires lots of hardware that has to be implemented at the full rate. In particular, you need something to generate this sine and cosine. Okay, remember, e to the minus 2 pi j f naught t is cosine 2 pi f naught t plus or minus j times sine 2 pi f naught t. So if you're going to implement this in hardware, this thing's weird. If you're going to implement this in hardware, you would need to generate the sines and cosines. That's not trivial. And Oh, and then you would have to build these low-pass filters. Again, not totally trivial because you'd be up at the, well, no, I guess these would be baseband analog continuous time low-pass. These are continuous time low-pass filters. But still, it's quite a bit of hardware. And then, if you want to do this complex, obviously you would need two A to Ds, one for the real, one for the imaginary. Okay? So that's why I say, but still this method requires a lot of hardware, two A to Ds, two low-pass filters, two cosine sine generators for this, and then plus the multiply. So quite a bit. But what I wanted to show you with bandpass sampling, this thing is tricky, with bandpass sampling is something that's much simpler, provided your A to D can support it. And this is what is called bandpass sampling. And in bandpass sampling, basically you don't need this, you don't need this, all you need is this, okay? So X sub C comes in, get rid of this, and just go right to your A to D. That's all you need to do. And this is the pretty part, guess what? The A to D doesn't have to run at a gigahertz or whatever F naught is. A to D can just run, and that's the best part. The A to D can also run at the 10 kilohertz rate, okay? So what we're going to do is not baseband this. We're going to just sample this at this rate. Effectively, we're going to ignore aliasing. We're going to alias the heck out of the signal, but in doing so, we will recover the baseband signal because that's all we're interested in. So suppose we again sample X sub C directly at Fs, okay? And let's take a look at the DTFT of X sub n. Now, I know this is laborious going through this formula. I understand that, but I tell you, this formula, the frequency domain sampling theorem, okay, it's very, very powerful, and it helps if you just, what am I saying, domain sampling, sampling formula that we derived actually 2 lectures ago. It's very powerful, and at least pictorially you should kind of get used to it. Especially look at your homework, especially like I said, the last problem. Okay, so you can look at this, and I've written. Well, actually, I've written. I've expressed this first of all, in like we originally learned it, in terms of a little omega. This is, remember, we're relating the DTFT of the sampled signal back to the CFT of the continuous Fourier transform of the original signal. I can write it like, or can express it in terms of that X sub C, you know, the guy at a gigahertz, or I can express it in terms of X sub B using that formula that I just had mentioned, right? This formula, okay? So I can plug that formula in for X sub C, and I can write the whole thing in terms of X sub B, the continuous Fourier transform of X sub B, the baseband part signal, okay? And I can further, also by using Fs equals 1 over T, right? Then I can write it in terms of F sub S. And that's the formula, okay? That is the formula. So that relates the DTFT of the sampled signal to images, lots and lots of images of the superposition of all those images of the baseband continuous Fourier transform of the baseband signal. Okay? So that's just using the sampling form. So I strongly encourage you to get at least familiar, you know, like I said, in homework 4, you can see some examples of applying this and just kind of get used to what it is showing, graphically at least. Now suppose, and here comes the pretty part that I mentioned before, that instead of sampling at the conventional rate, remember I said Fs was greater than or equal to 2F naught plus delta omega over 2 pi. That's equal to 2 f max of the original signal. Okay, and it still has the f naught in there. But instead of doing that, you know what we're going to do? We're going to get rid of this. We're just going to sample it at delta omega over 2 pi. See? Basically what we're doing is, if you look again at the baseband signal, we're going to do the same thing we did before. Remember when we did all this? Forget all this stuff. We're just going to, and we sampled it at fs greater than the bandwidth, basically. We're going to do that again here, so we simplify the A to D, and we're going to get rid of this, so we simplify all that hard work. So that is our new scheme. Just to make sure, okay, this is a picture. It's a pretty simple picture of T. That's going to go right into our A to D, and out is going to come x of n, and the sample rate here will be anything greater than or equal to basically the bandwidth, delta omega over 2 pi. Pretty simple, pretty simple. Beats the other approach all to pieces. This thing is very, very simple. But now the question is, okay, I like that. That looks simple, but then what are you going to get? Are you going to get this baseband signal out just where you want it? The answer is pretty close, but not quite. So we sample x sub c with a sampling rate matched to the bandwidth of x sub b. So what are we going to get? Well, here is our DTFT picture. Okay? So here's what we're going to get. Here are all the images. And if you notice, I've drawn this image from minus pi to pi. There's going to be a slight, in general, there will be a slight frequency offset. See? There will be a slight frequency offset when we sample this by f sub s. Since 2 pi times f sub s is equal to delta omega, there will be no overlap between images because we're going to get, let's see, what the hell did I do? Okay, I guess that's true. So there, you'll see an image here, you'll see another image there, and another image, but because 2fs equal delta omega, there is no overlap between the images. In fact, they just touch. So if you look at these, all these images in the sum, and this is a good example for you to look at or work out, if there's a slight frequency offset, what you will find is that generally there will be, these images will not touch. There will be an infinite number of them, but they generally could be off-centered just slightly, about omega equals 0. Okay, but the baseband image, this one here, and this image occurs, remember, here is the formula. It turns out that if you look at this formula for a while, look at this version of it. F sub s times summation k equals minus infinity to infinity of x sub b of omega times fs plus 2 pi. All this falls right out of the sampling formula minus frequency domain sampling formula. It looks like this, okay? So when k is equal to f naught over fs, or I should say the nearest integer, then you're going to get one of the images of this right at omega equals 0. Generally, that's what you're interested in. Now, it turns out that f naught over fs may not be an integer, in which case you're going to get a slight offset. But none of these images will touch, and you will get all of the information. But the baseband image is not exactly centered at omega equals 0. But whatever you miss here, you will pick up over here, see? So you will get all the image. It's just that they will not necessarily be centered at omega equals 0. And the reason why is because when you look at the frequency domain version of the sampling formula, please take a look at that. Get familiar with it. you will find that if f naught over fs is an integer, then there will be a k value, namely equal to f naught over fs, such that this goes to 0, and one of the images will exactly be the baseband centered at omega equals 0. Okay, and that's generally the image you're interested in. Okay, now, but the baseband image is not exactly centered at omega equals 0, but you will get all the information, and you do not have to sample it at that super high sampling rate. You can just sample it at the baseband rate. But the difference is when we did this approach, where was that approach? This approach. When we did this approach, which was computationally much more involved and more hardware, we were able to center the baseband. We were able to center this x sub b of t right at baseband. Okay, so everything's perfectly centered. Okay, if you're not careful in how you sample this, as long as you avoid aliasing. If you're not careful though, and if f naught over fs is not an integer, then you may get, as I said here, the baseband image will not be exactly centered at omega equals 0. So you may like to have it so that after you sample it, it is centered. So let's go a little bit further. Suppose f naught over fs is an integer, okay? So we're going to suppose that f naught over fs is an integer. So this ratio will be an exact integer, and we will get, for that particular value of k equal f naught over f sub s, we will find that there will be, for that k, this added term will go to 0, and we will get exactly the baseband signal centered at omega equals 0, which is generally what we want. So let's go a little bit further. Suppose f naught over fs is an integer. So we choose the carrier frequency to be a multiple of the sample frequency, or vice versa, better way to look at it. We choose the sample frequency to be a submultiple, some submultiple of the carrier frequency, f naught. So suppose we can choose fs equal f naught over L. Now, in practice, when we build these bandpass sampling systems, we actually do center the signal and the sample rate so that we do get this nice integer. Assuming we get this nice integer, f naught over fs is some integer, then guess what? Here's what it looks like after we've sampled. It's very pretty. We get this is the DTFT of the sampled signal, and lo and behold, we get exactly a baseband version centered at omega equals 0, and it's perfectly centered. Okay? So as long as we can choose f naught such that fs or f naught such that fs over f naught over fs is equal to an integer, then everything works out great, and everything's fine. Everything lines up, and we automatically generate the correct baseband signal simply by sampling at fs equal delta omega, provided fs is equal to f naught over L. Now, the next question is, and no cosine and sine generators or multipliers, minimal hardware, this is a complex version of bandpass sampling. And if you choose to, you can look at this in the time domain. And in the time domain, remember, we had this relationship, x sub c of t is equal to x sub b of t times e to the 2 pi j f naught t. Just sample at t sub n equal n over fs, where f sub s is equal to delta omega over 2 pi. Substitute that in, and you get this result. Okay, so we're going to sample at these instances, x sub n equals x sub c of t sub n, and where fs is equal to 1 over t sampled like this. And when you do that, you get this relationship. Essentially, you get, I don't know if you can read this. If you have your notes, you can see it. But basically, this is x of n is equal to x sub c of n over f sub s is equal to x sub b of n over f sub s times e the 2 pi j f naught n divided by f sub s, okay? But when f sub s is equal to f naught over L, right? When f sub s is equal to f naught over L, then, and I've done this a lot of times, so I'll let you see this, or here's my analysis of it. Anyway, when this is the case, when these two are related by an integer, then f naught over fs will be equal to L. So you have e to the 2 pi j n times L. So that goes to 1. So this goes to x of n. In this case, goes to x sub b of n over fs. So it's just equivalent to having sampled x sub b of t at the magic frequency, okay? And again, you can do all of this. It doesn't require any multipliers, any cosine and sine generators, or digital or analog low-pass, continuous time low-pass filters. All it requires is an A to D, or in the case of complex, 2 A to Ds operating at pretty much the bandwidth of the baseband signal. So it's a very, very slick way of doing this, and it's called bandpass sampling. At JPL, in the radio we right now have that's on the Mars Reconnaissance Orbiter, that's a digital radio, software defined, that's implemented using bandpass sampling. So it is a very, very powerful technique. So, and one more comment, quickie comment. So sampling x sub c of t at fs equal f naught L is equivalent to sampling x sub b of t at fs equal f naught over L. Furthermore, if fs is equal to delta omega over 2 pi and fs is a submultiple, so in other words, if fs, which is the bandwidth, if the bandwidth of the signal happens to be a submultiple of the carrier frequency, then that's great. Then we derive the correct unaliased sampled signal, okay? Now, it may be that, unfortunately, maybe f naught is not a submultiple, okay, or equivalent. It could be that the sample rates, because if we choose the sample rate that satisfies its match to the bandwidth of the signal, and it's a submultiple of f naught, then we get this nice spectrum in the DTFT. But it could be maybe these two constraints are very hard to meet, but that's okay. That's all right. If we can't meet these two constraints exactly, we can get rid of equality here and just say f, as long as fs is greater than or equal to delta omega over 2 pi, then we're okay. Okay, we're fine. Everything is still okay as long as fs is equal to a submultiple. So we have a little flexibility. You know what the only difference is? The picture will look like. So this is the picture with fs equal f naught over L. So what I've done is I've said, well, look, I'm going to make the sampling frequency a little larger than the bandwidth, but I'll choose it though so that it is a submultiple of the carrier frequency. What happens? You get this picture. Everything's fine. You just get a little bit larger gaps between the images. Now we still get the correct baseband spectrum with a little extra frequency spacing between images. So we can replace our original two conditions on the sample frequency with these two conditions. And that's all I will say about bandpass sampling. Very powerful technique. And I will note one thing, that a good tutorial on this for real signals, I put a paper here, that's good for real signals, because of course you're not going to send a complex signal over a channel unless you have two separate channels, one for the real, one for the imaginary. So generally you have a real signal, and there's a good paper on that for any of those who might be building a system or need to build a system, and you're interested in bandpass sampling. And here's another comment 2, if that's the case. If any one of you here or listening to me is watching the video is interested in building a bandpass sampling system, there is one caveat on this. And the caveat is this: even though you only need to sample your A to D converter, let's see if I can comment of this. If I have any, actually I don't. But in any case, the caveat is that even though the A to D converter can be sampled at the bandwidth of the baseband signal, even though it's centered up at some high frequency, the A to D would have to be capable of sampling at the carrier frequency, i.e. it's what is called its bandwidth must be as wide as F naught. So he said, well, if that's the case, then why not just operate at F naught? But by running it at the slow frequency, sample frequency, it consumes a lot less power. So this is still a good way to go. But what this is saying is this: here's my x sub c of t. Now it's going to have very, very high frequency components in it, but you know this will be modulated by some baseband signal. So what you're going to do when you bandpass sample is you're going to sample it here, maybe you're going to sample it way over here, you're going to sample it way over here, and yes, you will aliasing, but as long as you're sampling it faster than the bandwidth of the baseband signal, you recover it. But the key is, if this A to D is basically jittering a lot, you're going to miss the frequency peaks of that high frequency sine wave. So in any case, that's something to look out for. It's a caveat. But if you're interested in any of this, then I would encourage you to read that signal. You don't have to worry about this for this class, obviously. That was just an aside. But for those of you who might be interested in building or applying bandpass sampling. Okay, now the final thing that I want to talk about before we move on to the DFT, if you look at the notes on sampling part 2, those notes, there's several topics. One is the polyphase filters, one is bandpass sampling, one is something called polyphase filter banks. I will talk about those. And then there was a bunch of notes on A to Ds. I won't have time to cover that, or we won't be able to cover the DFT stuff, which will definitely be on the final. It's very important. So I apologize for that. But I do want to talk briefly about polyphase filters. Our project might be based on these. So there is something called, I'll just write these for a second, then we'll come back. Polyphase filter banks. So it's another application of polyphase filters, and it's used for polyphase filter banks. What are polyphase filter banks? What is an application? Well, I'll tell you what they are in a sec, but here's an application of these filter banks would be for what is called frequency division. Again, you have to copy this down. This will be scanned in, but just to give you a little motivation for this, multiplexing, okay, or that's called FDM, okay, FDM. So I'm just giving you a little motivation. And here would be an example. Suppose you had a signal, a digital signal, and its DTFT magnitude comprised a lot of non-overlapping components. So you might have here, this is omega equals 0. So here is, I'm going to sketch this frequency in first. Let's call that omega 1 equal 2 pi over m, all the way out to ... omega sub m, which we will make that 2 pi times m minus 1 over m. So it's almost all the way up to 2 pi. Or if you don't like this 2 pi, we know that everything wraps around at 2 pi. So this 2 pi times m minus 1 is equivalent to looking at minus 2 pi over m. So these can be thought of as the negative frequency components. Now this will generally be a complex signal, so these will be, and if you will indulge me, I want to make that closer here. Omega 1 equals 2 pi over n. So here's your input spectrum. Maybe you have a signal occupying this region, okay, where this is 2 pi over 2m bandwidth, or pi over m. Okay, so let's say you have a signal occupying this bandwidth. Now you say pi over m, that's kind of a small frequency band. No, but this is normalized with respect to the sample frequency. So it all depends on what the sample frequency. So let's call that signal 1. Signal 1, maybe it's voice. Okay, now there's going to be another signal, doesn't overlap. Its spectrum's going to be over here. We will call that signal 2. This is in many ways how multiple signals are transmitted over a channel. And then etc. You'll have signal 3 all the way to generally m of these signals, okay? And they're all separate. They don't overlap, but they're all separated in frequency. So I want to recover each one of these and then process each one of those. Now traditionally, oh, okay. All right. Traditionally, how do we do that? Say I wanted to do that digitally, okay, traditionally, we would do the, sorry, right over here. Traditionally, our architecture would be this. X of n comes in. Okay. X of n is our input. This is very, very wide band. This is wide band. And it is a composite, it's a wideband composite waveform. What do I mean? I just mean it has all of these frequency components in it. Okay, so this is the wideband. I'll call that X of n. Now what I will do is I will split X of n up into all these channels. This channel, I will multiply it by e to the e to the minus j omega naught n. That will go into a low-pass filter, H naught, and that will go in, and then, oh, by the way, I can downsample it, okay, because obviously this signal has a narrow bandwidth. Its bandwidth is limited to pi over m, so after I've low-pass filtered it, okay, I can downsample it, and out comes my output. Call that, I don't know, whatever you want to call it, y naught of n. Now, I'll do the same thing here. In general, I'll take this in, I will multiply it by e to the minus j omega sub k n, go into my low-pass filter. Guess what? Since I mixed it down to omega equals 0 baseband, I can use the same low-pass filter, and I again downsample that by m, and out comes y sub k of n, okay? And these omega sub k, as you can see from above, are just defined to be 2 pi k over m for k between 0 and m minus 1. So that encompasses frequencies from 0 to pi and pi to 2 pi, which actually correspond to negative frequencies, etc. So this is my traditional way to, how can we call it? This is my traditional filter bank, which basically demultiplexes. This is called frequency division. We multiplex it at the transmitter. This is demultiplexing it into the individual signals, 1, 2, etc., at the receiver. So this is what a filter bank does. Now, this is a traditional implementation of a filter bank. Again, it requires mixing with these e to the j's. These are the cosine generators. It requires filtering, and then it requires downsampling. So all of this is done from here on back at the high rate. Okay? It isn't until after you get past this step that you can actually operate down at baseband at the low rate. Well, once again, isn't there a simpler way to do this? And once again, polyphase comes to our rescue, and the answer is yes. There is a very, very much more computationally efficient way of implementing this bulky filter bank using a polyphase decomposition. So, just so you're exposed to this, we won't spend it. So I only have 2 pages of this, so there's not much. But now we can go back to the typewritten notes. But let's see where I'm at. There is a much more efficient way of doing this, and it is called the polyphase decomposition, and it's called polyphase DFT filter banks. Okay, given that we have discussed polyphase filters and decimators, subsampling, let's see how to build what is called a polyphase DFT filter bank. Actually, if any of you are interested in these filter banks or delve into it, there's a lot of stuff on these, and I'll be damned if I haven't forgotten. This is Mitra section. I forgot what section it is. I'll find it out though. But anyway, it's in the book if you want to follow up on this, or there's a lot of references in Mitra's book if any of you are interested in this area. But I'm going to give you one flavor of these polyphase filter banks. This is called a critically sampled. I'll explain why in a few moments. Okay, so what we want to do, we want to implement a decimation filter, but we want to precede it by a frequency shifter. Okay, so you remember this from before. If we wanted to change the downsample to data rate, we'd have to filter first, right, to prevent aliasing, and then we would subsample. Okay, well, that's what we're going to do here. And by the way, we already talked about a polyphase structure that could implement this much more efficiently. Okay, what we're going to do here in these 2 pages, promise that's all there is, we're going to introduce one more piece to the puzzle and create this output. Now, if you think about it for a second, if you think back, oh, I just came right to it. With the polyphase downsampler, it looked like this, right? All we wanted to do was basically just downsample a signal. How many outputs came out of the polyphase downsampler? Here was the structure we talked about more or less last time. One output. One output. That's it. That's our downsampled signal. Okay? Okay, in this structure, we know, just based on what I said before, that we don't have one output. We have M outputs. Okay? So whatever we come up with in terms of simplifying this had better have M outputs. And in general, here they are. So we're going to put this frequency multiplier in front here. This is e to the minus j omega k n mixer, if you want to call it that. And we will generate an output y sub k of n. And we're going to do that for 0 less than or equal to k less than or equal to m minus 1. So we really want to generate all these outputs. So we're going to do that with one structure, and it'll be much simpler than the conventional approach. So now if the input is centered at one of the discrete frequencies, or near one of these frequencies, the above system will first shift it to baseband. That's what that guy does. And then it will decimate. It will reduce the data rate by sampling, low-pass filtering, and then subsampling. Okay? So let's do this operations. Let's work out the math. This is basically working out the math. And what we find is that I'm going to call this signal x sub k of n. Okay? And instead of repeating this, hopefully you can read this. You can read it in your notes. Basically, what I'm doing is I'm saying x sub k of n is going to equal to this signal, which is x of m times e to the minus j omega k m, or it could be n, whatever you want to do it, convolved with h. That's this filter. That's the output right here. Okay? So I've just expanded this out for you. I've just expanded the convolution out into the infinite sum, and so that's what that piece is. Summation m h of n minus m times x of m times e to the minus j omega sub km. Now I personally like to rewrite this. Instead of taking h of n minus m, I like, by change variable, like to write this as summation index of h of m and then put the n minus m inside here. So I can do that. Okay? And then all I'm going to do is subsample that. Okay? So I'm going to take y sub k of n will equal x sub k of n times m. And that's what that looks like. So I've expanded that out for you. And all I've done is replace n in here with little m, with little n times big M. Okay, that's the decimation operation. So you can go, please go through this. The math is pretty simple. And when I do that, you also have this exponential, e to the minus, let's see what that looks like, j omega sub k times n times m minus m. That's this term up here. M is the summation index in the convolution. Little n is the time domain index. Okay? So this is equal to e to the minus j omega sub k n times m times e to the plus j omega sub k times m. Okay, what I'm going to do is this is the only one that depends on little m. That's the summation index. This is independent, so I'll move him out front. So he's right there. And I will keep everything in there. So we finally end up with this. Summation h of m times x of n times big M minus m times e to the j k of m. Oh, wait a minute. No, wait. There was a factor out front. E to the minus, where'd that go? Where'd the factor go? What was that factor, by the way? What was that mass man? Who was that mass man? There was a factor out front. E to the minus j omega sub k times n times m. Where'd that go? Is this right? Shouldn't there be that factor there? Now, think about it for a second. Look at that factor. I'll give anybody here $300 so they know where the factor went, or why it went away, or if it can go away. Well, think about it. What is omega k? 2 pi k over m. Aha! So the big M here cancels the big M down there and the omega sub k, and you're left with e to the minus 2 pi j times some integer. That's one. Notice that in the last line, we set e to the minus j omega sub k n times m equal to 1. Why? Well, now you know why. But like I said, it's only one, really, it's 2 pages. Please go through this. It's very instructive. Okay, now, so we have this as an infinite sum, h of m. We've reduced it to an infinite sum, h of m, blah, blah, blah. So now what I'm going to do before I finish this is I'm going to do the old polyphase trick. I'm going to let that index m, I'm going to write that as L, another integer, times m plus p. See? And L will go from, well, you can read it here, minus infinity to infinity. It's just an integer, but p will be constrained. 0 will be less than or equal to p, less than or equal to m minus 1. See? That's our old polyphase trick that you've seen before when we talked about polyphase filters. This is more or less the same thing, except we're souping it up to accommodate this multiplier here and to generate m output channels. So I'm going to do something which seems seemingly Makes things more complicated, but in the end, it won't. What I'm going to do is I'm going to replace that single sum with this double sum, and I'm going to move things around a bit, and I'm finally going to end up with this result, that y sub k of n is equal to summation L equal minus infinity to infinity. I'm just rewriting this last line, so you don't have to write that if you don't want to. P equals 0 to m. The inner sum is finite, times h sub p of L times x sub p of n minus L times e to the j omega sub k p. Okay? So basically, if you look at this inner sum, and let's see something. Okay. Well, let me go to the next page, and the final page, by the way. Where in the last line we have defined, what is this h sub p? It turns out the h sub p, which is going to look something familiar, is equal to h sub p of L. Okay, hopefully you can read that up there, is going to equal to h of L times m plus p. Seen that before? Yeah. The h sub p are the polyphase components of that low-pass filter H. Okay? So that's that. And what else? And what I'm calling x sub p of L, I'm calling this x, see this x sub p of n minus, or x sub p of n, what is that? X sub p of n is just, let's see, what did I call it? Of L, I guess that's the time index, is just equal to x of L times m minus p. Okay? So all that falls out of that formulation, just less than a page. And interchanging the order of L and P, in the last line we have the final result, namely yk of n. I'm just switching the use, and you can see exactly how I derived it. P equals 0 to m minus 1, e to the j omega, what do I call it? Sub k p times the inner sum, L equal minus infinity to infinity, h sub p of L times x sub p of n minus L. Okay? So this is basically, this part here is just the convolution of those filters with x sub p. And then when you do the sum, this is like a DTFT. Okay? So you end up with this structure. And I would, we haven't talked about the DFT yet, but we will. And when we do, we'll come back to this. This is worth kind of looking at this architecture, especially if we have a second class project on it. But this is equivalent to the following structure. We take our x of n in, we do the delay, we've seen this before. So this is x of n minus 1, etc. Okay, we have these delays. We downsample them. So like, look at this channel. This is what I'm calling x1 of n. What is x1 of n? x1 of n is equal to the downsampled version of x of n minus 1 downsampled, so I put the m here. X of n times m minus 1. And doesn't that look just like this? Yeah, it looks exactly like this. These two are equivalent with p equal to 1, see? So this operation, delay, downsample, that's generating these components, okay? And then you go through these filters, which are the polyphase components of the original low-pass filter, okay? So you go through those components, and then you do something that we didn't do before. Namely, you go into what is called this operation here, which is an endpoint inverse DFT in this case. We'll talk about that later on, more to come. But the input, or the endpoint inverse DFT, what should I call this? I'll call this V naught of n. I will call it V1 of n. Let's call it B sub m minus 1 of n. And what the endpoint inverse DFT does is it takes the signals y sub k of n equals to, the inverse DTFT is just this, as we'll see later on, p equals 0 to m minus 1 of v sub p of n times e to the j omega sub k times p. That's what the inverse DTFT does. It basically, it's just like computing, it's sort of like computing the DTFT of these, but only over a finite range, okay? So that's what it does, and that's how it generates it. Now, as we will see later on, there are very fast ways, very computationally efficient ways of generating this. And guess what? Guess what? Suppose we wondered what is y sub 0 of n. What does that look like? Well, that's just summation p equals 0 to m minus 1 v sub p of n. Okay? And if I can get lucky, see if I get lucky here. Well, just a second. Here it is. Oh, shoot, that was on that page. And if you look at this, remember this decimator, where we took all the outputs and we just added together? That produced the decimated output, okay? So if we take this channel, where we simply just, the k equals 0 channel, all we're doing is we're just adding up, we're just doing a simple decimation, okay? Because if k is 0, if you look back at the original diagram, the k equals 0 corresponds to no frequency shifting. And that, if k were 0, this is gone, right? So you have x of n going to the filter and output. So this polyphase structure reduces to the polyphase decimator when k is 0. See? So this is this is generalization of polyphase decimator to a filter bank, okay, to an M channel filter bank. Pretty slick. Now again, I may have a project on this, so it'll give you a chance to study this a little bit more, understand it. But we're not going to do anything more with polyphase or filter banks or anything. I wish we could, because there's a whole theory on these, and people teach courses. There's a professor at Caltech, Vaidyanathan, who teaches an entire course built around these filter banks. So it's very interesting stuff, but this is as far as our journey into filter banks. Polyphase filters will take us for this class. Because I want to next get into, so in your in this sampling part 2 notes, there's a whole set of notes on A to D and D to A converters, which I wish I could go through, but I simply won't have time in this class, because if I do that, we will miss a lot of the DFT, which is absolutely critical. So we will skip that, and maybe next time. In fact, if you take, if I teach EE483 in the spring, you can take, oh no, guess you wouldn't want to do that, would you? You've already had it. But in any case, when I teach it during the spring or fall semesters, we have more lectures. So, anywho, sorry about that. We must move on, and as we move on, there's another set of notes. And you know what? I just uploaded these notes. This is, I forgot the name of them. But anyway, they were just uploaded on the 14th. So you will see them. So if you go to the, the usual place, course documents, I have uploaded these notes. They're just called, there's something called DFT EE483 DFT, something like new. Aren't you lucky? We have a new set of notes. And they were uploaded on the 14th of July. So they are available for downloading to your computer. And they are something called the discrete Fourier transform. To distinguish it, and you know what, I'm going to get out the book. I've had it with this thing because I don't know, I've never written down. And if you look at Mitra, and he kind of turns it around, but if you look in Mitra, multi-rate digital analysis, blah 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 blah, DSP. Here it is, chapter 5. We're kind of moving around the book here, but this is Mitra, chapter 5. And he talks about, well, it's hard to read that anyway. But anyway, he has a whole chapter on finite length transforms. And the one we want is the DFT, the discrete Fourier transform. Relationship between the DTFT and the DFT and their inverses. He covers that topic. Well, first of all, he defines the discrete Fourier transform. We'll do that. Then he talks about the relationship between the DTFT and the DFT. We'll do that. And circular convolution, I'll mention that. Classification of finite length sequences, I guess. DFT symmetry relations, yes. Discrete Fourier transform theorems, yes. Fourier domain filtering, yes, we will do that. And he also, I like Mitra because he has this section on short time Fourier transforms. We will talk about those. So we're going to cover most of the DFT material in Mitra chapter 5. So that is what we will cover. And I tell you what, why don't we just take a break? That makes the most sense. I will meet you back in 15 minutes. This is a good place to break, and we will continue with the DFT. So I will see you shortly. I have, if anybody else has homework. No, nobody else does, because I know I got emails from you two, so that is fine. So I will see you soon. Thanks. I'll just wait later. Whew. A lot of talking here. so much I want to cover. I think as you'll see, we have so much, I have so much material here that it's, I don't know how I could have covered in the summer the A to D stuff too with all the other stuff. But anyway, I digress. So now we're going to, as I said, we've jumped around in Mitra. The Z transforms were chapter 6. Now we're back in chapter 5. But this, to me, is a little more logical way to do it. Okay. So far, what we've talked about with the DTFT is pretty much an infinitely long transform. So, you know, when we did the DTFT, n equal minus infinity to infinity, x of n, we didn't really pay too much attention. We never paid too much attention to the fact these limits were infinitely long. Now, of course, in practice, we don't have an infinite amount of data. We just have a finite. So we want to, or we'll need to truncate this infinite sum off. And since most of our data is causal, I mean, it goes from 0 to n minus 1, this will gradually transitions into this. N minus 1, x of n, e to the minus j omega n. Okay? This is not the DFT. See, and that's another problem with digital signal, DSP, digital signal processing. There's all these acronyms. And there's the discrete-time Fourier transform, and then there's the discrete Fourier transform, or DFT. Those are two much different things. At this point, from here to here, that's not quite the DFT. In the DFT, there's yet another place where things are quantized or made discrete, and that's in the frequency. So let's talk about, or let's proceed to a definition. Okay, let x of n be a discrete function, and it's finite. It's or sequence, a finite length sequence for n equals 0 up to n minus 1. Okay, so that's your data samples. The DFT is see, the DTFT is a continuous function of frequency. Okay, little omega. It's a continuous function. The DFT is a discrete function. So it not only does it deal with finite length sequences, which we use, but it also deals with discrete frequencies. So I can write the DFT, I just call it x of k in the notes, summation n equals 0 to n minus 1 x of n. I can write it as e to the minus j omega sub k times n. So it kind of looks like what I said earlier was the truncated DTFT, except the frequencies are finite. And what are these frequencies? Omega k equal 2 pi k over m. And once again, for k between 0 and m minus 1. So that is the DFT. That's the definition of the DFT. So it's defined only for finite length sequences, which generally we have a finite amount of data, and it is discrete in frequency. And I tell you, it's completely different than the DTFT. And we'll, as we talk about it, we'll go through what those differences are, and how we can, more importantly, how we can interpret the DFT and how we can relate it back to the DTFT. So all those stuff all those topics we will talk about. Yes, okay. Huh?
Is n.
You said the
period of x of n is n from the definition. It's finite from n to 0 to n minus 1.
right, x of n.
So it's n. Its periodic of periodicity is n. So for x of k, the periodicity is n.
Yeah, I think that is correct, actually. Yeah, so the x of n goes from 0 to n minus 1. So as a function of k, you're saying, well, you're jumping ahead. That's good. That's good. I think, this is x of k plus n is equal to x of k. That's what you were saying. Yeah, that is correct. Yeah, there's a lot of, if you think about it, the DTFT is for an infinitely long sequences, and the frequencies are continuous. The DFT is finite length sequences with discrete frequencies. But when we talked about the DTFT, one thing that was pretty clear from the definition, that as a function, a continuous function of frequency, it was periodic with period 2 pi. Well, the DFT also has a discrete periodicity, and its periodicity is basically n, where n is the length of the DFT. So, and you could say, how did I know that, or how did he know it? Because just look at the definition. Replace k with k plus m, or k, I guess in this case that should be n. Is that what you were saying? That's what you were saying. Okay. You know why I couldn't pick it up? Because M, N, they kind of sound similar. Okay, I'm sorry. Yeah, you're absolutely right. Okay, so that should be a make it k equal 2 pi k over n. Anyway, these are the discrete frequencies where n is the length of the transform, and you can see if you let k replace k with k plus n, you will get this 2 pi periodicity in the makers of k, and therefore, since it's in the exponential, it'll be the same. So you do get this periodicity. But yeah, sorry. Anyway, that is the definition of the DFT. We have a lot more to, that's why I wanted to kind of move ahead, because I have a lot more to say about it over the next couple of lectures. Here is the inverse DFT. So in other words, if you have k, x of k from 0 to n, you notice that the k ranges, as I said here, from 0 to n minus 1. Little n ranges from 0 to n minus 1. Everything's from 0 to n minus 1. So if you have x of k, which is n length, actually it is periodic outside of that, then you can also recover the original samples, little x of n. So this is the inverse DFT. So just like the DTFT, there's a DFT and an inverse DFT. But they both involve finite sums. Now, in the case of the DTFT, the inverse was defined in terms of an integral. Here, since we're dealing with just finite exponentials, we only have a finite sum, not an integral, to define the inverse. X of n given by 2, by this inverse, is well defined for n greater than n minus 1 or n less than 0. And in fact, so in other words, what I'm saying here is this is typically defined for 0 less than or n minus 1. However, if n is outside that interval, you'll get some result, right? And the question is, what kind of result would you get if you let little n wander outside of this interval? You would find that if you let n be larger than n, you would find that x of n is periodic, i.e. x of n plus n would equal x of n. So in other words, what this generates is x of n is a periodic repeating sequence. So you would have something like this. X of n, n versus n. You would get something here, I don't know, 0, n minus 1, and then you just get the same thing again. Repeat it over. I don't do a very good job of repeating this, but this would just be periodic. If you evaluated outside of the interval 0 to n minus 1, okay? So, because some people say, gee, if I can, maybe this is predicting or extrapolating what x of n is. No, it isn't. It's just periodically extending x of n. That's all it does. So the only new information, or the only true information, is in this interval 0 to n minus 1. So there you have it. The DFT, the inverse DFT, they're both of length n samples in each of the DFTs. And if you try to extend it outside of that interval, you will get periodicity. What is the DFT? What kind of advantages? What are some basic properties? It is invertible, so that's good. Here's the inverse of it. It provides estimates of Fourier transforms of a sample analog signal. It is a finite length transform, so it's obviously it's made for actual applications where you have, you've collected a bunch of samples. You want to figure out what is the frequency content of these samples. Do I have noise? Do I have sine waves? What do I have? The simplest way, many times, simplest way to tell that is by using a DFT if you have a finite number of samples. And when you do that, it does provide an estimate of the energy, how it's distributed in frequency. So that's, but only with finite samples. So that's another advantage. And the third advantage of it is that, which I don't know how much, if we'll talk about this too much, but it may be computed very efficiently using, here's another acronym, discrete Fourier transform, the fast Fourier transform, the FFT, which you've undoubtedly heard of. In fact, MATLAB doesn't have a function called DFT. MATLAB only uses FFT. So if you try to look for DFT in MATLAB, you won't find it. And the FFT is computed just like the DFT, except it's done very efficiently. So you might have something like this. X, that's an array of samples. You might say FFT of little x, okay? Where x and x are both vectors of length n, okay? So if you have a vector of length n, you want to do a DFT, you call the FFT routine, and it will compute. Both x and little x will be of length n. But be careful how you interpret the frequency, because you want to know, well, gee, do I have a frequency at 20 hertz, 30, whatever it is. Be very careful in how you interpret the frequencies of what you're getting out from the DFT, or in MATLAB, the FFT. And what I mean by that, I will explain later on. I'll very carefully go through that. So you have to be careful how you interpret the output, but yes, there is a DFT. In fact, you have to be careful how you interpret the output of a DFT in general, as we'll discuss. Okay, what are some properties of the DFT? Well, one thing is, it's related to the Z transform, or basically the DTFT. This doesn't say much. It just says that if we have a finite length sequence of data and we want to take the Z transform, then we would compute something like this. X of z equals summation n equals 0 to n minus 1, x of n z to the minus 1. If the input sequence truly was finite length, that's how we could compute the Z transform. And you can relate this x of z. Now remember, this is defined for all, well, it's defined for all values of z in the complex plane. And if you look at it, this is going to be, if I expand it out, it'll be x of 0 plus x of 1 z inverse plus dot 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 plus x of n minus 1 times z to the minus n minus 1. I've written it out like that just to illustrate the fact that there are really, it's a finite length, so there are really no poles in the z plane, or zeros, except at, so only what? Only, I guess only poles at z equals 0. So that's the only place you get poles because you have inverse power z. Everything's fine as z goes to infinity. We talked about that before, but there are no other poles. So that's x of z with a finite length sequence. Then the DFT of x of n, you could relate it to x of z if you wanted, by x of k equals x of z equals e to the minus 2 pi j k over n. So in other words, if you computed the z transform using this formula of the finite sequence, then all you'd need to do is evaluate at discrete points along the unit circle, and the values that you get out at these discrete points are basically the DFT samples. DFT of x is a z transform of x evaluated at n equally spaced points along the unit circle. Similarly, for the DTFT is the same thing. The DTFT, which is of the finite length sequence, n equals 0 to n minus 1 of x of n, e to the minus j omega n. Now that's if you only had a finite length sequence, and the same thing, if you evaluated it at e to the j omega sub k, where omega k is 2 pi k over n, that would be the DFT. So all of these signals are related. It's just that before we were treating with the z transform of the DTFT, we were treating the input as being infinitely long. So now we've restricted everything to being finite. And we have discrete frequencies. So there's some differences, a lot of difference between the DFT and the DTFT. But we'll find out what those differences are. I'll show you how to use the DFT for frequency analysis. That will come. What else? Here are some basic properties. We have the linearity. That's pretty clear. The DFT is a linear operator. It's a linear transform, so that's no big surprise. Circular shift. Now here's a new one. Since the DFT, or the inverse DFT, leads to periodic discrete time sequences. Remember what I just said. The DFT, the inverse DFT, that generates x of k from generates little x of n from x of k, right? So it's a way of going this way. And the resulting x of n that it generates is not just defined between 0 and n minus. It can be computed for all n, but when you do that, you find that x of n plus n equals a little x of n. So typically just one period is computed. And vice versa for the DFT. The DFT is also periodic. X of k is equal to x of k is x of k plus n. So anyway, these are all these sequences that are defined from the inverse DFT or from the DFT itself are essentially periodic with period n, the length of the sequences. So, having said that, since the DFT or inverse DFT leads to periodic discrete time sequences with period n, the length, we can only perform circular shift operations on finite sequences when using DFTs. Well, that's a new one. So what the hell am I talking about? Well, let's see. So we will let x of n be a sequence defined over 0 and n minus 1. We define a circular shift by n naught samples on x of n. Now before, see, we never had to, now things are getting a little bit more interesting. Before, we just talked about what I will call a linear shift. We had x of n, we had x of n minus L. Linear shifts, no problem. Linear shifts are very simple to understand. You just delay the signal by L samples. But now we are in the world of finite length sequences. And so, and also the DTFT of x of n minus L, we had a simple formula for that, right? E to the minus j omega L times the DTFT of x of n. Well, we still have something like that with finite length sequences, but it's a little bit more interesting, I guess you could call it. Okay, so instead of these simple linear shifts, we have to first of all define a circular shift by n naught samples on the finite length sequence x of n. See, we have to define that, and here's why. If we tried to do x of n minus n naught, right, for x of n finite, what would happen is, let's take n naught equal 1, and let's let n equal 0. That would imply that x of minus 1. What is that? What is x of minus 1? No idea. You want to assume it's 0? You do that. You want to assume it's periodic? You could do that. But generally, you don't know what this is, see? X of minus n. In the DTFT, like what I was talking about before, the DTFT, when I, or the Z transform of the DFT, that's kind of implicitly assuming that, well, actually, this isn't making any assumptions on, no, I'm sorry, this really isn't making any assumptions on X of n. But the problem with finite length sequences and linear shifts, we don't know what they are outside of the interval 0 to n minus 1. When you do a linear shift on a finite length sequence, you're going to very quickly get to values of the index that you don't know what the values of x are. Okay? So instead of that linear shift, we don't want to do that. We will define a circular shift. And what is a circular shift? And the circular shift properties are perfectly well defined. You only end up with samples that you know what they are. So here's my notation. I don't know, Mitra might use something a little bit different, but I call this capital CS sub n naught of x. And by that, what I mean is it's a circular shift by n naught samples on the finite length sequence x. And here's the strict definition of it. It involves a modulo function, okay, modulo n. Now, MATLAB has that built in, so you can test. Most of you have seen it, but if you haven't, the modulo function, and that's n minus n naught, modulo n. The modulo function has this amazing property that no matter what n minus n naught is, no matter what it is, that n minus n naught modulo n will always end up being between 0 and n minus 1. That's a beautiful. Thank you. It wasn't you guys. I was afraid that was going to happen. You could hear them outside, so hopefully they'll let me finish the lecture. Give me 30 more. That's all I ask. So no matter what n minus n naught is, if it could be minus 1 like it was before, minus 10, whatever it is, the modulo makes everything okay. It always puts this back in the interval 0 to n minus 1. So what is, in general, what is n mod n for any n? It's whatever n is, the result is between 0 and n minus 1, I'll call it n prime, such that n prime plus some multiple of n is equal to the original input n. Okay? So here's an example to see what I mean. If you haven't seen that, most of you I'm sure have. But if, for instance, big N were equal to 8, little n were minus 1, then minus 1 modulo 8 would be 7. Why? Because if I let k equal 1 here, minus 1 plus n, in this case 8, would be 7, and it's in the interval from 0 to 7, okay, 0 to n minus 1. So the point is that, you know, what is k? That's not important. It's just some integer such that, and you can always find this integer, such that whatever n prime is, some multiple times big N plus n prime will always be in that interval 0 to n minus 1. And if you want, you can use our old trick again. You could always write n is equal to k times n plus p. Remember that trick? Where p is between 0 and n minus 1. Okay, so that's what the mod is doing. It's basically finding the p, okay? That's what the modulo function does. So that's very nice. Now we can prove the following circular shift theorem for DFTs, okay? So, y of n, I will let that be the circular shift version of x circularly shifted by n naught samples. It's defined to be this. And y of k is the it's the DFT of y of n. And as it turns out, to be proved, possibly by you guys, that the DFT of the circular shifted version, look at it, it's equal to this. Well, we actually didn't prove this theorem, but we can. Possibly you will, as a homework exercise. But in any case, this is our circular shift theorem. So what it says is that x of, well, I like circular shift of little x, or I'm sorry, little x by n naught samples, which is equal to x of n minus n naught mod n, corresponds in the DFT domain to, let's see, e to the minus j omega k n naught times the DFT of the original sequence. So, and where omega k is again equal to 2 pi k over n naught. So this is sort of looking like, this result here sort of looks like what we found with linear shifts and the DTFT. Okay? So we were hoping that if we shifted, if we did a time shift in the time domain, that we would get this phase shift in the frequency, well, in this case, the discrete frequency domain. And you do, no problem, but provided that instead of a linear shift, it is a circular shift, okay? And by the way, before I move on, I have a little, not all of my notes are, some are typed, some aren't, so I apologize for this. But here's another way of thinking of the circular shift. These are also in your DFT notes. So consider a discrete finite sequence. The circular shift by k samples is defined just like that, like we were talking about before. The best way to think about the circular shift is as a simple linear shift of the periodic extension of x of n. So that's another way to do it. If you don't like the mod function, just take x of p of n to be equal to the periodic extension of x of n, okay? So that's going to be, you just break it up 0 to n minus 1, 0, and then n to n, 2n minus 1, etc., 2n minus 1, and then just take and repeat x. If it looks like this, repeat it again, and so on. Oh, it's horrible. Anyway, you just repeat it on and on, backwards too, so that you convert x of n into an infinitely long sequence, albeit periodic. And then you apply a regular linear shift to this periodic extended infinitely long sequence. That's also the same thing as the circular shift. So you can think of it like that. Or if you want to get fancy, you can think of it as a big wheel. I like to think of it like this. You can think of the circular shift by considering a wheel with all the samples of x distributed equally about the wheel. And then if you want a circular shift just by n naught samples, just turn it like this to n naught ticks, and what you end up with will be the circular shift. If it's negative, you turn it back this way. And the value that pops up at the wheel, it's a wheel of fortune. Okay? It's just a big wheel of fortune. So anyway, just hope you don't go bust doing this. So if you want to go to Vegas, you can do that. Whatever you want to do. All for you. All for you. Anyway, so that's what the circular shift is. And the circular shift theorem for DFTs, which I promise you, you'll prove it one way or another. You'll see the proof one way or another. You may do it. Just simply says this. The DFT of a circular shifted version is this phase factor in the DFT domain, discrete frequency domain. Okay, We'll come back to that in a little bit. I'll come back to that. Some other properties. Oh, this is an interesting one. This is an interesting one. You remember, for the DTFT, I'll write it down here at the bottom. Recall, DTFT symmetry. DTFT symmetry. Remember this? If x of n is real, you recall this, then, from the midterm too, x, that's the key, x of e to the j omega is equal to x of e to the minus j omega complex conjugate. You recall that. Here, you recall that, okay? Well, this is a symmetry property for the DTFT. Well, there's a comparable property for the DFT, but it's a little bit more involved. And yet, it involves these circular shifts again. You can't get away from them. If x of n is real, then you have this symmetry property that x of k turns out to be the same thing as x of n minus k modulo n complex conjugate. Meaning, what that is saying is that there is complex conjugate symmetry about k equal n over 2. You might say, why isn't it x of k is equal to x of minus k complex? Wouldn't that make more sense? There is no minus k. There is no minus k in the DFT. There's no negative indices, so you can't do that. So all you have is this crazy circular shift. And you might ask, well, that's right. That's right. So here's a picture. This is a picture with n even. You get this picture. If you look at n even, as it turns out, x of n over 2, and x of 0, both of those points are real, as it turns out, if the input sequence is real. X of 0 is real, and x of n over 2 is real. Why? Why is that? That's simple to see. Because x of 0 is just k equals, or n, equals 0 to n minus 1 times x of n, right? E to the minus 2 pi j omega k, but k is 0, so that's 0. X of n over 2, so this is real, if x of n is real. This is equal to 2 e to the summation x of n, e to the minus 2 pi j k times n divided by 2 divided by n, okay? And it turns out that's real, because that's just, this thing is just minus 1 to the k. So this is also real. So anyway, take a look at that. You should convince yourself of that. So these points are real, but there is a complex conjugate symmetry around this point. So like n over 2 plus 1 is the same as n over 2 minus 1 complex conjugate, and so on and so forth, okay? Now my question, I will leave this as a question, and I just thought of this question, so I have no idea what the answer is. I think the answer is false. But what about this? This is just for you to think about. Is x of k equal to x of minus k? I know, I said there was no minus k, but there's this, right? Mod n. Is that true? I don't think it's true. I don't know. I just thought of the question. So I'll put a big question mark here. I'm not sure about this. Minus k mod n, is that the same as x of k complex conjugate? I don't know. I'll leave that as an aside. But this is true. This is definitely true. There is complex conjugate symmetry about the midpoint if n is even, right? Because if n is even, this is a good integer. If n is not even, n must be odd. There's only two. That's the neat part of this finite. There's only two possibilities for n. If it's not even, it's odd. And if it's odd, you have the same type of symmetry again. except that it's symmetry about, like, there is no middle point. It's n minus 1 over 2 times n plus 1 over 2. And those points are all integers, okay? So there you get that complex conjugate symmetry. There is no n over 2 point, but there is still k equals 0, and yes, x of 0 is still real, okay? So that's symmetry properties of the DFT. Now here's an interesting property. Just a minute. Hopefully, did I? Give me a second here. See if I. Yes. Yes. Okay, I just wanted to make sure. Did I put that in here? No, I didn't. So I'm glad I looked back at my own notes because, okay. So those properties, I didn't prove them, but they are straightforward to prove based on the definition of the DFT. Now here's an interesting one. Circular convolution theorem. This is related actually to Ymax, as I will show you in just a second. Circular convolution theorem. We define a circular convolution for two sequences of length n as this, okay? So it's basically, it sort of looks like the regular linear convolution, except once again, it's got this mod function, and it has the mod function. We assume that x and y are both of finite length n. It has the mod function because, again, y is not defined outside of 0 to n minus 1. So it's sort of the counterpart. It's the counterpart of the linear convolution where there would be no mod function. We assume that we know what x is outside of that interval. Whether we assume it's 0 or whatever we assume that when we do the linear convolution that we assume that y of n minus m is known. But here, it's not known outside the interval, so we slap a mod n on it, and we call that convolution with a big circle to denote this has got the mod function. This is a circular convolution. So one thing you notice is that x and y are both of finite length, n, and you will notice that z of n is also, well, that's not clear. We'll come back to that. Z of n is also, it's not really finite length, but it is periodic. And I will prove that later on. But I'm trying to see, well, sorry here. Oh, no, I don't. Okay, I'll have to go back to those other notes. So, property 1, circular convolutions. Z of n is periodic with period n, capital N, okay? Now, that may not be obvious from that. If you want to try to prove it on your own, you can. I have the proof of that back later on these notes. I'll point out where that is. Property 2. If little z is equal to x circularly convolved with y, then guess what? Z of k in the DFT domain is the product of x times y, okay? And vice versa, if z, little z in the time domain is the product, then in the frequency domain is a convolution. So this is kind of the theorem that you were looking for. This is the counterpart of the theorem that we derive for the DTFT. With the DTFT, if we convolve two sequences, a regular linear convolution, then we got product in the DTFT domain. In the DFT domain, that kind of still works, except it's got to be a circular convolution. Then we get that property. And by the way, if you buy, you remember that property that I didn't prove, that I'm going to leave it up to you, I think, or show you directly. You recall, that I mentioned this, that if y of n is a circular shift, then in the DFT domain, it's this phase product. Well, you can use that and prove, using that, you can prove this result. Simple. So suppose z of n is the circular convolution of x and y, so it looks like that. Then just take z of k, and x of m is the summation, m is the summation index. So in this case, you can just take the dft of this, but that's just a circular shift of y by m samples, so that's going to equal the dft of the circular shift will just be the dft of y without the circular shift times that phase factor. And now you can take the y of k out since it doesn't depend on the summation index, and you're left with y of k times this sum, but that sum is just x of k. So anyway, that's the counterpart of this linear shift theorem for DTFTs, okay, and convolution. Okay, now before we end, yeah, this is a good place to mention this, although I have to apologize. I thought I made a copy of this, but anyway, I guess I didn't. Okay, as I mentioned, this is also related to Ymax signals, or not signals, but the Ymax. I don't know if do any of you know what Ymax is? What's the other one? Wi-Fi? Ymax. Okay, well, Ymax and Wi-Fi are standards which a lot of your cell phones use. Actually, there are improvements or advances in this Ymax. But it's based on, the Ymax is based on something built around the DFT. Oh, I just have one page. All right, well, I'll show you that. It's built around the DFT, and it's built on something called OFDM, orthogonal frequency division multiplexing. And this is what a lot of these cellular standards are based on. But the problem is you have these, you want to transmit a signal from me to you, or further, you have all this channel multipath stuff that you've got to contend with. So at your receiver, you're going to have to figure out the channel. Well, what people do when they're using a finite length DFT transform as part of their signaling, they use something called a cyclic prefix. This, by the way, is right out of Wikipedia. You can look this up yourself. Look at Wikipedia and type in cyclic prefix. This is also interestingly discussed in Chapter 5 of Mitri. He talks about this. So what OFDM does, what this Ymax standard does, it introduces a cyclic prefix. Cyclic prefixes are used in order for Ymax, or this OFDM, in order to combat multipath by making channel estimation easy. What it does is, because in the channel, like due to multipath, what you have is you have a signal, call it S of n, but it goes through this channel, call that H, okay? And out comes Y of n, I guess, which is equal to H convolved with S. And that's linear convolution. Linear convolution, not, I mean, you know, physics doesn't, this is all physics. All physics knows is linear convolution. It doesn't know how to do in a channel like this circular convolution. So you've got to figure out a way of somehow making this linear convolution look like a circular convolution. Well, you know what? You can't change the channel, but you might be able to change S of n and make it look more like it could come out of a circular convolution. So here's what the cellular companies who use this, these standards, Ymax or Wi-Fi, what they figured out to do. And it's just not cellular, it's like your computer systems use a Wi-Fi standard. So anyway, they figured out to do something. They said, well, look, as an example, consider a system which has n signals, or or length n, of n. The message can be written as d0, d1, d sub n minus 1. Those are the points in the DFT, or the IDFT, either one, but they're finite length. The symbol in OFDM is constructed by taking the inverse discrete Fourier transform of this. That's what, because at the other end, the receiver, you take so you take the DFT of this, and then back at the receiver, you take the, you take the inverse DFT of this, and then back at the receiver, you take the DFT, and then you recover all these data points, D0, D1, etc. But again, the problem is this goes through this channel. So here's what the WiMAX people did. What they did is, after they take the inverse DFT, they don't send that, but they append to the inverse DFT, which is endpoints, right? They append what is called a cyclic prefix. And basically, if we let the output of the inverse DFT be denoted as x of 0 all the way to x of n minus 1, what they do is they append L samples, or I'm sorry, L minus 1 samples to the beginning of this input. And what are those L minus 1 samples, you may ask? Well, what they are the last. If you take this, this is an array, it has endpoints in it. Take the last L samples of this array, take the last L samples of this array, move it back to the beginning. See this? There it is, mathematically. So now they have a new symbol with a cyclic prefix. Call that x. So the basic symbol with n samples that you would get out of the inverse DFT, you call x naught. But the actual signal that's transmitted over the channel is this signal, which has, it's of length L plus n. It has the last L points of this appended to the beginning, and then it has the end points, okay? So that is what is called the cyclic prefix. Now, why would they do this? What would be the point of doing this? Well, if you assume that the channel, say it's represented by an FIR filter of some length L, okay? Now, again, you're going to take the output, which is this extended signal with the cyclic prefix, and that's going to go through the channel. Linear convolution will be the output, okay? Thus, after linear convolution with the channel, which happens like this, you don't see a mod in there, right? But this is equal to circular convolution with the original sequence, as x of m minus k becomes x of m minus k modulo n. And why is that? Because, like, if we have a negative sample, well, we've already done the wrapping when we created this cyclic prefix. This took this extended signal, and so if I want to know what, in the linear convolution, if I need an x, see, here's the linear convolution. Suppose m were 0 and L was 1. Then we want to know what x of minus 1 is. Well, guess what? Now we kind of have it. If we take the modulo, that x of minus 1 would be n minus 1. Well, you know what? N minus 1's right there. Isn't that nice? So when we take this sequence and we look at x of n minus 1, there it is. We build it right in for you. So that all of these signals, x of n minus 1, x of n minus 2, they are all given, they're all contained in this extended vector. So what that means is the net result is that the DFT of the DFT of x of k, or I'm sorry, of y of m, y is just equal to, the DFT is just equal to the product of h times x, where x is the discrete Fourier time transform of little x. That's that extended sequence. Thus, a multipath channel is converted into a, just a scalar parallel channels in the frequency domain. In other words, the multipath, even though you're doing the DFT, just looks like a product of h times x, and the task of channel estimation, all I have to do is figure out what the h's are, divide them out, and you've got the original signal. And after you've got the original signal x, okay, so if you can take y and divide it through by an estimate of h hat, then you have an estimate of x hat. After you have this estimate, do the inverse DFT, throw away those samples you don't need, and everything's fine. So this is used in OFDM and WiMAX. I will tell you what, well, I'll scan that in. But anyway, if this is an aside, only if you're interested in knowing how these cyclic or these circular convolutions can actually be used in practice. I didn't do a great job in explaining it, but you can go to the site. But I'll scan that in. So,
pardon me, Professor. Only
yes.
5 minutes left.
Oh yeah. Okay. Well, Jesus. We'll just stop there. I can't go too much faster. But anyway, please sometime sooner than later, I will post the second project. Probably make it due during the final. You can turn it in at the final. That way it gives you about a month, 3 weeks. And I promise you all, the second project won't be the first one had all these 15 parts. The second one won't be like that, so you won't need quite as much time. And also, I will post a homework set covering probably the sampling part 2 and maybe the DFT. Okie doke. I will see you all next time. Have a good week.